All righty, you guys, BC Calc students, here we are. I have another lesson for you. We're moving into chapter 5, and this is a demarcation between doing derivatives and doing antiderivatives. The two are obviously mathematically related. One undoes the other. There are a lot of specific details. Many of you asked in your questions from when it said make a list of 5 questions, a lot of you asked about what are the rules for, anti-differentiation? How do you undo a derivative? And the answer is some you just memorize, and then a bunch of others. There's all these techniques we're going to learn to do this. But of course, why would you bother doing an antiderivative unless there was some reason to do it? And so I want to give you a little motivation today of why people would bother doing an antiderivative in the first place. When would you ever use this stuff? So today is a rectangular approximation method, which is really kind of crazy. In order to approximate the area under a curve, you guys can imagine a shape like this. You're going to, probably break it into trapezoids and what have you. But at some level, the folks who invented calculus were sort of lazy to the extreme in a weird way. They kind of said, yeah, I'm not going to bother with trapezoids. I'm just going to break everything down into rectangles. And no matter how complicated the shape is, they're like, we'll just use rectangles for everything. And what's funny about that is, as long as you have an infinite number of rectangles, the area of all the rectangles added together will exactly equal the area under the curve, which is really kind of remarkable to think about. Well, how could that be? And we'll be looking into that in this unit and in this section. We'll see how that works. So when would you ever look for the area under the curve? Okay, this method is called the rectangular approximation method. It's used to find the approximate area under a curve because we're going to use finite rectangles. We're going to have a finite number of actual rectangles, and so we can only approximate the area of a complicated looking curve. So one immediate place it would be helpful if you were given the velocity of an object. So if you're given the velocity of an object here over time, 5 hours, or the velocity of this object over time, what's amazing is the area under that curve, that shaded area, tells you how far the thing has traveled, okay? If you think about it, if you do the rate miles per hour times hours, you can't avoid it. You get an answer that's in miles, okay? Same thing here. This axis here is in miles per hour. This axis here is in hours, and so it's unavoidable. If you take miles per hour and multiply by hours, you get the total miles, which is a really cool concept. So if the velocity were constant, you guys know that this is the formula, distance equals rate times time. The problem is that formula only works as it stands if the rate is a constant. And so in this case, that would correspond to a rate of 50 miles per hour. And then the time would be 5 hours. So time is 5 hours. And so if you did distance equals rate times time, you would say, well, let's do 50 miles per hour times 5 hours. The units of hours cancel, and you get 250 miles. So this graph here represents that area under there. You might say, well, that's square units. And in some ways it is, but not really if this is in units of miles per hour and that's hours. That area is literally a distance that this person or object traveled in that 5 hour period. So what's really cool is if you don't look at it as this formula here, rate times time, and you simply talk about the area of this shape, you'd say, well, I know what the area of a shape is. It's the base times the height. In this case, the base is 5 hours, and the height is 50 miles per hour. And so we're calculating an area, which is kind of crazy. This ends up being 250 miles. And so it's a little weird to call it the area. In fact, it's the displacement or distance that the object has traveled in that 5 hour time period. So what could you generalize this? What if instead of having a simple shape like a rectangle, would it work if you had more complicated shapes? And the answer is, of course, it's calculus. Of course it will work. So what we can do here is break this shape down into other pieces, okay? I suppose I could do a trapezoid, a rectangle, and a triangle, but it's late in the afternoon and my brain is tired, and so I'm gonna do that instead, okay? So what I'm gonna do is break this shape down into multiple areas, okay? Let me call this area 1, area 2, area 3, and area 4, okay? And then I just add those all up. Now, When I say area, those are in fact distances because it's miles per hour times hours, okay? So area 1 is equal to the base, 5 hours, times the height, 10, 20, 30, 40 miles per hour. And that equals 200 miles. So this area under here represents 200 miles that this thing has traveled, okay? Area 2 is base times height over 2. So what's the base of this? Well, it's 5 hours again, times the height of this is 10, 20, 30 miles an hour. And then I divide that by 2. And what would that be? 150 divided by 2, 75 miles. So that takes care of area 2. Okay, area 3 is base times height. It's 2 hours times 50, 60, 70, times 80 miles per hour, or 160 miles. So that takes care of area 3. And then finally, area 4 is another triangle. So it's 1/2 of the base, 1, 2, 3 hours, times the height, 1, 2, 3, 4, 5, 6, 7. Okay, wait, I said 80 over here. I messed up. 1, 2, 3, 4, 5, 6, 7. Okay, so I screwed up here. This isn't 50, this is 40. So 1, 2, 3, 4, 5, 6, 7. So that should be 70 there. That's 70, and that gives me 140. Okay, now I'm questioning everything. Area 2 was indeed 30 by 5, so that is correct, divided by 2. So we're good here. Okay, so area 4 is 3 hours, 1, 2, 3 times 1, 2, 3, 4, 5, 6, 7 times 70 miles per hour. And this would be what? 210 divided by 2, 105. 105 miles, which I just think is cool. Okay, so then we add those all up. We have, I'm going to do 275 plus 140 plus 105. Okay, and I hope I didn't screw up, you guys. It's late in the day and I'm tired. I hope I did that right. So we get the total area. The distance is equal to 520 miles. So that's the distance represented there. Okay, if I screwed up, I'll catch it on the next video. Okay, I'll come back and I'll say, oopsie, I made a mistake. But that's the idea. Okay. All right, and so then here, in some cases, the area under the curve might be best estimated with a series of smaller rectangular areas. For these situations, we must decide how many rectangles or subintervals to use, and then we have to decide what's the height of each rectangle. And we generally would look in 3 places: the left edge, the middle, or the midpoint, and the right edge, okay? So in this example, you'll notice this shape I can't break into triangles and rectangles because there's always going to be some overlap, or I'm going to overestimate or underestimate this area. And so that's where calculus takes us, is it's going to allow us to actually calculate the areas exactly. So right now in this example, suppose we want to estimate the area under this curve. So I graphed this on Desmos using this particular function on the interval from 0 to 4. Okay, and we choose to use 4 subintervals. The table function in our calculator may come in really handy here, so that's sort of a hint. Let's type that in. Y equals clear. Let's type in what? 3 plus 1/2 x squared, right? And there it is. Okay. All righty. So we have 4 ways to do it. The left edge. So what we're going to do here is we're going to divide this. It goes from 0 to 4 into 4 rectangles. So we're going to go like this: 1, 2, and then 3 and 4. Okay, but what do we use to represent the height? Okay, you guys would probably say, well, I would estimate somewhere in the middle here. But strictly following a left edge, a left rectangular area method, we're going to do this here. Okay, well, what's that height there? Well, if I plug in x equals 0 into here, I get 3. So that first rectangle has an area of 3 times 1, which is just 3 square units. It's an underestimate because there's this little piece that I've not accounted for here. Okay. All right. The next one that I put in here, again, we're going with the left edge, is this rectangle here. Well, what height is that? I suppose I could eyeball it. It looks like it's 3.5, but we should really work it out. This is x equals 1, and that's the left edge of this one. So I put a 1 in there, and sure enough, I do get 3.5. So this second one has an area of 3.5 times a width of 1, or 3.5 units. So again, that's an underestimate. There's this little bit here that I've not accounted for. Okay, at 2, that's the left edge of this third one, right? And it looks like it's at 5. If I put a 2 in here, I would have 3 plus half of 4. So 3 plus 2 is indeed 5. So that area there would be 5 times 1, or 5. Okay, and then and again, it's an underestimate because I am not accounting for this section here. And then finally, this last one, it looks like that's a what? An 8? It looks like a height of 8. Let's try it. Put a 3 in there. No, it's not 8. That's actually not quite right. If I put in a 3 in here, I have 9 halves. 4.5 plus 3, that would actually be 7.5 times 1, or 7.5 units. So what's funny about that is it really looks to me like that hits at 8. And so that's kind of funny to me. If I go to the table and I type in a 0, a 1, a 2, and a 3 in there, these are the areas that I got. Because remember, the width of the interval is 1. So 3 times 1, 3.5 times 1, 5 times 1, and 7.5 times 1. And so now it's just a question of adding those up. So I add up the 4 areas, 3 plus 3.5 plus 5 plus 7.5. And so I end up with a total area of 19 square. Oh, I'm off the paper. I'm sorry. 19 square units. Okay. That's an underestimate, and you're going to be asked why that is. And it has to do with the concavity, or it has to do with the derivative. This function is increasing here. And so because this function is increasing here, if we go at the left edge, the right edge is always going to be taller. And the problem is we're not accounting for that additional area. So this is an underestimate. Okay, because the curve is increasing. Okay, the graph is increasing. All right. Okay, midpoint, M or midpoint. Okay, so now we need to evaluate the height of this one. What we do is we take the midpoint of this rectangle to decide the height. Okay, it's a little weird. We don't average this with that. That's not what we're doing. We average the two x values. So this is 0 and this is 1. So what's the average? That would be x equals 1/2. And we use that point to determine the height of that rectangle. And you might say, oh, that's perfect, because this area will exactly match that area. That doesn't always exactly match. But if I go back to my table and I type in 0.5, that's the midpoint of this interval. And that tells me that that height is 3 1/8, 3.125. So this first rectangle's area is 3.125 times 1, which is just 3.125, right? Okay, and then the second rectangle, it would be here. Okay, now where do I find the midpoint? This is not a segment, so we're not looking for the midpoint of the segment. We're not looking for the midpoint in the y direction. We're looking for the midpoint in the x direction, and that would be x is 1.5. So that next rectangle, I would type in 1.5 here, and that is a height of 4.125. So that second area is 4.125 times 1, because that's the area of a rectangle, base times height. And so let's see, 4.125 is right in there. So that second area is 4.125. Okay, the third rectangle is here. Okay, and again, the midpoint in the x direction, this is 3. That would be 2.5. So if I get my calculator and type in 2.5 in here, I get 6.125. Okay, so the third area is 6.125 times 1, which is just 6.125. And then finally, the fourth one, the midpoint would be 3.5 in the x direction, so 3.5, and that gives me 9.125. That is area 4 is 9.125. Okay, so I'm going to add all of those up. So we have 3.125 plus 4.125 plus 6.125 plus 9.125. Now, this is a more accurate estimate of the area, 22.5. So this area is 22.5 units, okay? And so then it may ask you, is this going to be an overestimate or an underestimate? And that gets a little tricky if you're going for the midpoint, okay? So does this area cancel and so on? In a moment, I'm going to show you how to get the exact area, and we can come back and decide if this was an over or underestimate. Okay, well, you guessed it. The third method is to just take the right edge of each interval. And so we're still going to break this thing down into 4 rectangles using the exact same dividing lines. What's different this time, though, is that we're going to decide to use the right edge of the figure. So the right edge of this one is at 1, this one's at 2, this one's at 3, and this is at 4. And so that first rectangle, you can see it's going to overestimate that area. So if I go back to my table and I put in a 1 in there for x, right? I'm sorry, 0. The very first rectangle, actually, oh, no, we're doing the right edge. We're doing the right edge. So I'm going to put in a 1, and I get the area of the first rectangle is 3.5 times 1. Okay, the area of the second rectangle, that's this one. I want to use the right edge again. So area 2, I put a 2 in here, and I get 5. So 5 times 1. Okay, area 3 is the third rectangle. The right edge of that one is here. I think we worked at that earlier, as that was 7.5, right? If I do a 3, that would be 7.5 times 1. Okay, and then the last rectangle is here. That looks like that's at an 11. I use the right edge of the interval. So if I put in a 4, I end up with an 11. So the fourth area is 11 times 1, okay? And so what I do is I add all of those up. Okay, since they're all multiplied by 1, I don't really need to do a lot of work in my calculator. I'm going to do 3.5 plus 5 plus 7.5 plus 11. And now I end up with 27 is the area, 27 square units. Okay, so I suppose this is pretty predictable. This is the worst underestimate, and this is the worst overestimate. Okay, and then I am curious, is that really the average of the two? I'm just curious. Sometimes it will work out and sometimes it won't. Do I get that average of the two? No, not quite. If I average these two extremes, I get 23, and this says 22.5. And so for this particular curve, I do not get the average of the two. The midpoint is not just the average of these two other ones. Okay. All right. I can't help myself. You guys are sitting in a calculus class. I want you to have like the answer of how this whole problem works. So we're soon going to put a star next to this. It's going to ask you about this on the homework tonight. We're going to soon be calculating the exact areas under the curves using antiderivatives. And if you simply must know the exact area under the curve, what you need to do is think of this function as the derivative of some other function. And we usually use a capital letter. If we call this f of x, what we typically do is we call the antiderivative of this capital F of x, okay? And what function would have this derivative? Well, I think it would be a 3x, right? And then this would be, I need to raise that to the third power, so that would be x cubed. I'm going to leave the 1/2 in here, but when I just raise this to the third, I have to divide this by 3, like so, okay, to get everything to work out. Watch. If you do 3x plus x cubed over 6, if you take the derivative of this, you end up with that, right? The derivative of this is 3. The derivative of this would be 3 times x squared over 6, which is equal to 1/2 x squared. And so we're doing this correctly, okay? All right, some of you are sitting there going, hey, don't forget that there's a constant here, okay? And we don't know that constant yet, okay? So let me say that. That is our antiderivative there. And I don't have an anchor to determine what value of c to use right now, okay? The way you work this out, the way you do this problem is pretty cool. What you do is you evaluate that antiderivative function at 4 and subtract it evaluated at 0. You just do the right edge, work it out, minus the left edge, work it out, okay? So what I'm saying is the area, the exact area, is big F of 4, because 4 was this end of this interval, and then 0 f of 0, you subtract those two. This represents an area minus an area, and you end up with an area total, okay? And this is the exact answer. So you just put a 4 in here. So that would be 12 plus 4 cubed is 64 sixths plus c minus, and now you have to put in a 0 in here. Well, that's not too bad. You put a 0 there and a 0 there, and you just end up with c, okay? And what's kind of cool about this is we ended up those c's canceling. And so the exact area of this, I'm going to assume I'm going to get a number pretty darn close to 22.5, okay? Because this one was the midpoint. I bet that one's pretty accurate. Let's work this out. I have 12 plus 64 sixths. That would be 12 plus half, 32 thirds. That would be 36 thirds plus 32 thirds. And that is equal to what? 68 thirds? Okay. And 68 thirds, gosh, that's like 69 thirds. It would be 22, what, 22 and 2 thirds? 22 and 2 thirds. Let's try that out. 68 divided by 3. We get 22 and 2 thirds indeed. Okay. And so you guys can see that this method of using rectangles to approximate areas, I mean, I only did 4 rectangles. Okay. And I got 22.5. Okay. And then I used an infinite number of rectangles. And this is a lesson from calculus. And I got 22 and 2 thirds. Okay. Instead of 22.5, I'd have 22.66, okay, or 0.67 or whatever. So that it's really remarkable how accurate that method can be just using rectangles. So that's the focus tonight. We're just going to use rectangles. Okay, I'm worried about my internet and the length of the video and the sound quality and everything, so I'll meet you at the next video. Okay, you guys? All right, take care. Okay, bye-bye.